right, so let's go ahead and go over a problem that was related to Wednesday's lecture, which again you saw at home. Something like this will be on the exam, so that's why it's worth going over this one more time. I'll give you the equation. Okay, I'll give you this equation. I'll give you the constant. All you need to know how to do is use it for the test. So this topic is vapor pressure. All right, so just very quickly, because I don't want to go over this, and fall behind. Let's say you have two liquids. Okay, a liquid that is going to have weak IMF, okay, is going to have a high vapor pressure because it can easily evaporate and it could easily condense. Okay, that's what you need to know. So weak IMF will have a very high or exert a high vapor pressure. You know pressure, right? Okay, pressure is exerted by a gas. Right, so what is a weak IMF that we learned here? Dispersion forces is a weak intermolecular force. Okay, something that has strong intermolecular forces okay, here we're talking about hydrogen bonding, ionic bonding, okay, H bond, which is polar. Okay, there's polar and then there's polar plus hydrogen bonding, right? Remember? Okay, so this is going to have the same phenomena. So the liquid will evaporate to a vapor, and that vapor will exert the vapor pressure as it comes back down to a liquid condense. Okay, so condensation, evaporation, condensation, evaporation. Okay, so which one would have the higher vapor pressure? Which is easier to form a vapor? The one that's held together by weak intermolecular forces or strong intermolecular forces? So this is going to have a high vapor pressure. And which is easier to form a vapor? Something that has weak intermolecular forces or strong intermolecular forces? Okay, it's easier to form a vapor when you're held together by weak forces. It's harder to form a vapor when you're held together by strong intermolecular forces. Okay, so that's the key. Okay, this is a pressure. All right, this is a pressure. All right, one thing that you have to know is that vapor pressure is quoted at a specific temperature. You change the temperature, you're going to change the vapor pressure. Okay, so this is temperature dependent. Many things in this class are going to be temperature dependent. So if I have a temperature T1, it's going to have a vapor pressure. Okay, we were talking about liquids here. I change that temperature, I'll have a new vapor pressure VP2. Okay, so all this comes together in this equation here. Okay, so this will be on the exam, and we'll do we'll do one practice problem over that, and then we'll resume our normal notes. Alright, so something like this will be on the exam. So Wednesday's video, the quiz, your homework, and this should cover this topic well. Alright, the chlorofluorocarbon refrigerant trichlorofluoromethane has a vapor pressure of 100 millimeters of mercury at minus 23 degrees C, and it has a delta H vaporization. So this delta H vaporization is the energy required to vaporize 1 mole. Okay, how much energy do you have to put in to get it to form a vapor? Okay, how much energy do you have to put in to get 1 mole? To get 1 mole to form a vapor. This is delta H vaporization. Okay. So the question here is, what is the normal boiling point for trichlorofluoromethane? Okay, anytime you see normal on the exam, short answer, whatever it may be, okay, we're saying 1 atmosphere. 1 atmosphere. Okay, so normal boiling point, what's the pressure? 1 atmosphere. Normal freezing point, what's the pressure? 1 atmosphere. So normal means 1 atmosphere. It's actually the, I think, standard pressure that's here, okay, where we are now. Okay? The pressure on our atmosphere now is 1 atm. Okay, so normal means 1 atmosphere. So this becomes a plug-and-play type of problem, similar to the exam or your quiz. You just plug it and play it into this equation. Right, so we have a vapor pressure P1. I'll call this P1, 100 millimeters of mercury. Okay. And P2, I'll call this P2. Let's put it in a different color here. Normal. What did we say normal was? 1 atmosphere. Okay. So normal boiling point is a pressure of 1 atmosphere. Okay, normal means 1 atmosphere. Okay, so the energy is 24,770 joules per mole. So one thing I want you to know is that we're going to convert delta H vaporization to joules per mole. The reason why we convert this to joules per mole is because our constant, just given, you can't change the constant, is joules over mole Kelvin. So to get the units to cancel out, let's convert this to joules per mole, and this is going to be multiplied by 1,000. This is how you do it. So you're going to take 24.77 kilojoules per mole That's the conversion factor. So this becomes 24,770 joules per mole. Okay, so this is our delta H vaporization. Okay, so that's what we're going to put in here. R will be given on the exam, so you don't worry about it, okay? I'll throw out the problem if I don't give you R, or I'll give you R. So that's 8.314 joules over mole Kelvin. All right, 1 over T2. So what is T2? That's what we need to find, 1 over T2. Because we have P1 at T1, we need a P2 at T2. Temperature, T is temperature. All right, minus 1 over T1. So what is 1 over T1? Okay, minus 23 degrees C. So step 2 here is that we want to convert this to Kelvin. So convert all temperatures to Kelvin. Okay, does anybody remember how we get to Kelvin? Okay, we add 273. So you can add 273.15, you can add 273. I'll just add 273. Okay, why do we convert to Kelvin? Because our constant has units of Kelvin. So what's minus 23 plus 273? Let's quickly do that here. I'm getting 250 Kelvin. Okay, let's put that over here. So we need to solve for the red T2 temperature. All right, couple of things here. We don't put units inside the natural log. Okay, don't put units inside the natural log or the log. Okay, that's just some math thing. So we're not going to do that. So we're going to add the units later. Okay, we'll add the units later. All right, I can't speak. How would we attack this problem? Okay, how will we attack this problem? So this now becomes an algebra situation. This is where some students get it wrong. So we're going to solve for T2. How will we do that? What we can do is, so this is the same thing as natural log over 100. Okay. All right, and then I'm going to take this 8.314 joules over mole Kelvin, and I'm going to multiply. I'm going to multiply both sides of the equation. And one more thing here, you guys, is the units. Okay, the joules over mole cancels with the joules over mole. This Kelvin will eventually cancel out with that Kelvin, but our final units are going to be in Kelvin. Okay, our final units are going to be in Kelvin because temperature is in Kelvin. So I'm going to take this 8.314 joules per mole Kelvin, but the joules per mole will cancel, but I'll just keep the units. I'll carry the units. Okay. Everyone see what I'm doing here? Okay, I'm going to divide by 24,770. I'm going to divide by 24,770. Joules per mole. Okay, so multiply by the blue, divide by the black, keep these subtraction as one entity. My T1 is this, my P1, my P2, and then T2. Alright, so multiply by the blue, divide by the 24,770 joules per mole. That's going to equal 1 over T2 minus 1 over 250. Right, now I'll cancel my units. The joules over mole cancel. This Kelvin actually goes back in the new denominator. Alright, let's do this on our calculator. Alright, natural log of 100 times 8.314 divided by 24,770. I think. All right, I'm getting 0.00155. Let's put some extra digits in there. Actually, the units are Kelvin. The Kelvin goes down. Or you add the units later, which equals 1 over T2 minus 1 over 250. So what I'm going to do now is I'm going to take this minus 1 over 250, I'm going to put it to the other side. I'm going to put it to the other side. Again, this is just a math problem, not chemistry. 0.001546 divided by Kelvin. Okay, plus minus 1 over 250K goes back to the other side, so that becomes plus 1 over 250K. Okay, this equals 1 over T2. Okay, we're trying to solve for T2 here. Right, take that minus 1 over 250, move it to the other side. All right, so I'm going to do 0.001546 plus 1 over 250 Kelvin. Okay, this is what I'm going to do on my calculator. 0.00154 blah blah. Okay, plus 1, I like my parentheses, 1 divided by 250. And that's going to be 0.005545. 46, okay, equals 1 over T2. All right, and to solve for T2, it's going to be 1 divided by this 0.00546. Okay, by the way, this is divided by Kelvin, just the units here are Kelvin. So my final units are also going to be Kelvin, okay, when I cross multiply. This is cross multiplication. All right, so what's 1 divided by this? Do you see this little x to the minus 1? Okay, that does the reciprocal. Or you can just go ahead and do 1 over this number. So about 180.3 Kelvin. Okay, another thing that students trip up on is the units. Okay, this is going to be Kelvin. We'll just do 180 Kelvin. All right, this is our final answer. To get it to degree C, what will we do? We will take 180 Kelvin. Sorry. What we will do is to get to degree C, we will take 273 minus 180. And it's about 93 degrees C. And this is our answer. Okay, so from here on out, it's just math. Okay, so make sure you are good with the math here. Okay, get the temperature to 93 degrees C, and this refrigerant starts to boil. In our refrigerators, it will never get to 93 degrees C. Okay. All right, so this is how we do this problem. Okay, let's ask another variation of this problem. Okay, I want to ask you, the question is, what will be the vapor pressure Let me ask you this question. What will be the vapor pressure not at minus 23 degrees C, but 23 degrees C, room temperature? Okay, what will be the vapor pressure at room temperature, which I'm going to call 23 degrees C? Okay, can we do that problem? Can we? All right, let's see if we can do that. All right. Okay, we'll do this one more time. But now I want to ask you guys the question, what will be the vapor pressure at 23 degrees C of this refrigerant? Okay, not minus 23 degrees C, which we know the vapor pressure will be 100 millimeters of mercury. Okay, what will be the vapor pressure at room temperature, which is about 23 to 25 degrees C? Okay, can we do this type of problem? All right, let's go over this, and then we'll move on to the next part of the chapter. All right, we still have this at 100. This time we'll solve for P2. Okay, the delta H vaporization is going to be 24,770 joules over mole. Okay, the R will be the same at 8.314 joules per mole Kelvin. Okay, what's 1 over T2? Okay, we're going to take our 23 degrees C and add 273 to it. Okay, that's 296 Kelvin. And our T1 here, this is T1, P1. Our T1 here is, what's minus 23 plus 273? 250. So this is a very different scenario than this practice problem, because now we have to solve for P2. Okay, how will we solve for P2 when it's inside that natural log? Okay. So here's how we'll do that. Okay, do you guys know how to do this on our calculator? All right, very different algebra. Okay, that's all. Okay, I'm going to do this whole thing as one big chunk. So follow along with me on the calculator. Okay. So I'm going to do 1 divided by 296. We're asking for the vapor pressure at room temperature, 23 degrees C. Plugging everything in, this is plug and chug. 1 divided by 296 minus parentheses 1 divided by 250. Close the parentheses. Actually, you know what? I'm going to put everything in parentheses. I'm just kind of paranoid that way. Okay, 1 divided by 296 minus 1 divided by 250 is this. Okay, times 24,770. Okay, so 1 over this minus 1 over that is this weird number times 24,770. Everyone see this? Okay, is that weird number divided by 8.314. Divided by 8.314. And this is what I'm getting. Natural log of 100 over P2, which is what I'm trying to solve for. Okay, equals this mess. Okay. Minus 1.85. I'm just going to add some extra digits here. Okay, just add some extra digits, and then we'll cut off at the final answer. I'll put an extra digit. Fine. Okay. And by the way, units, joules over mole, Kelvin cancel. All right, now question to you is, how do we solve for P2? Okay, so this is the point here where you're going to take the inverse natural log. Okay, this is the math where students mess up on. And what is the inverse natural log on our calculator? Very good. This is called E. Okay, which is E. Of both sides. Natural log and E are like flip that flop. Okay, if you flip, natural log. What if you want to flop? Take the E. Okay, if you want to flip, take the E. What happens if you want to go back? Take the natural log. Okay, so in other words, they're inverses of each other. Okay, so if I take E, and E on your calculator is to the power. E. Okay, this is not, you just do it on your calculator. You don't have to worry about any of this. So e to the power of natural log 1 over P2 equals e to the power of 1.852005. Okay, so what is e to the power of natural log of 100 over P2? Okay, what is it? Okay, it's a way to get it out of the natural log. Okay, you pop it out. You pop it out of this bracket. Okay, remember, no units inside the natural log or log. So it's a way to pop it out. You take the e, because they're inverses of each other. Okay, so this actually pops it out, and e to the power of minus 1.85 we will do on our calculator. Where is this natural log button? Okay, it depends on what calculator you have. Okay, every calculator will be different. Okay, in most calculators, it's the second to the natural log. Okay, second inverse or second or shift natural log, because you're not taking the natural log. Okay, you are taking the inverse natural log, which gets it out of the natural log. Okay. Second natural log. Okay, second natural log e. Okay. Right, some calculators have e by itself, so whatever calculator, make sure you know how to do the inverse natural log, which is the same thing as e. Okay, the inverse natural log is the same thing as e to the power, actually. All right, e to the power of, what's this number now? Minus 1.852005 is 0.15692. I'll just add some extra digits. Okay, now I'm going to solve for P2 here. Cross multiply. Okay, this is how we get the P2 in. So what will P2 be after we cross multiply? It's going to be 100 divided by 0.156922. And I'm getting about 637. Okay, that's a very high pressure. Now, what are the units? Okay, so on the exam, if you don't put units, okay, it's half a point deduction, because we want to put units. Okay, numbers by itself are meaningless. Once you put the units in, it conveys meaning. So what are the units? What's our final answer? 637 what? It's a pressure, not a temperature. Sorry? It's not atmosphere, because our units here. Yeah. Yes. Okay, millimeters of mercury. Should be millimeters of mercury. Okay, so pressure is in atmospheres or millimeters of mercury. They have it here as millimeters of mercury. You want to put the right units. And it's not atmosphere. It is pressure, but that's not the units. Okay, the units here are millimeters of mercury. And it's not a temperature. Okay, this is a pressure. Okay, so it's asking for a pressure, don't put temperature. If it's asking for a temperature, don't put a pressure. All right, can we do this on an exam, something like this? Okay, the key point here is E. E. Okay, what is the inverse natural log? It's called E. Okay, what are the units of pressure? Atmospheres is 1, but for this problem, what was it? Okay, millimeters of mercury, right? All right. All right, so if we increase the temperature, what do you think is going to happen to the vapor pressure, higher or lower? what happens if we raise the temperature here? What's going to happen to this dynamic equilibrium? Will it increase or decrease? Increase, yes, that's correct. So if we raise the temperature, what happens to the vapor pressure? It increases, all right? So vapor pressure, not only is it quoted at a specific temperature, but as you increase the temperature, you increase the vapor pressure. More becomes vapor as you increase the temperature. And as more becomes vapor, more vapor pressure is, exerted. It makes sense. Okay, increase the temperature, increase the vapor pressure. Okay, decrease the temperature, things slow down in terms of the motion, so you're going to decrease the vapor pressure. All right, let's go back to our notes here. Kind of went over this in class, so okay, this is something we did together, okay, in Wednesday's lecture, and then we went over a similar problem just now. Okay. All right, a couple more things before we kind of wrap up this chapter. So let's say we go from a liquid to a gas. Okay, liquid to a gas. The energy for that to happen, the energy for 1 mole for that to happen is called delta H vaporization. Okay, and for water, that's going to be around here. You don't have to memorize these numbers. I'm just giving them for reference. Okay, for water, the delta H vaporization is going to be 40.79. Okay, right? So the more intermolecular forces that you must overcome, okay, the more IMF intermolecular forces you must overcome, the higher this delta H value is going to be, this delta H VAP, delta H vaporization. Okay, more IMF, more energy, more delta H vaporization to overcome those intermolecular forces. This energy. Okay, you just have to know this delta H vaporization is an energy. Okay, if you have higher intermolecular forces, if our bonds are strong, it's going to take a lot of energy to break us apart as a molecule. For water, this is going to be about 40.79 kilojoules per mole. Okay, taking 1 mole of a liquid and converting it to a gas. That's what I'm showing here. Okay, if I take this same solid, okay, and convert it to a liquid, okay, take a solid and convert it to a liquid. Okay, what is solid going to a liquid? What is an ice cube? Is an ice cube solid? Okay, what happens if I convert it to a liquid? Melting. Instead of melting, let's use the word fusion. Okay, that's just the word they use, fusion. Okay, so fusion is a fancy word for melting. All right, so this is to melt 1 mole, okay, 1 mole. And that's the delta H fusion. Let's do the same thing for that, for water. For water, you don't need to memorize this, but for water, it's about 6.01 kilojoules per mole. So to melt 1 mole of water, it takes 6.01 kilojoules per mole. To vaporize 1 mole of water, it takes 40.79 kilojoules per mole. Delta H vaporization and delta H fusion. Okay, so what we can do here is that we can add these two up. Okay, we can add these two up. When we add these two up, we're going to add these two energies. Okay, when we add these two, energies together, we'll add the two add these two phase changes together. We will add the energies. Right. All right. So when we add these up, the liquids cancel, and we are left with solids going to gas. Okay, a solid going to a gas. This is called sublimation. Okay, anybody here eat banana chips or one of those things? Okay, so banana chips, or if you go to Fresh Market, they have these freeze-dried chips or freeze-dried vegetables. They put salt and pepper on them. Basically, what they're doing is they're taking like a banana. You chop up a banana. It's kind of solid, and there's a way to take that solid and convert all that water into a gas. Okay, so that's what banana chips are. A frozen banana, all that water deposits get converted to gas, skipping the liquid, and you get banana chips. It's called freeze drying. Right, this phenomenon is called sublimation. Okay, and so what is sublimation equal to? To sublime, or to from a solid to a gas, 1 mole of water or 1 mole of any substance. All you need to do is add the delta H vaporization. You add the delta H vaporization plus the delta H fusion. Remember, solid going to vapor is sublimation. Going to the back is deposition. But remember, these phase changes can go back and forth. All right, so this is something that you guys should know. Okay, just add the two energies together. 1 mole of vaporization plus 1 mole of fusion. Okay, gives you 1 mole energy required to sublime 1 mole. Move from solid to a gas. Okay, skipping the liquid. All right, the last 10 minutes, let's go over the heating and cooling curve of water. So let's do this now. Okay, so I do not know if this is true. This was told to me a long time ago, but they asked this on the MCAT. So if anybody's taking the MCAT, maybe it's good to know. So let's talk about this here. All right, so heating and cooling curve of water. All right, so first let's look at the axes here. On the x-axis is time. On the y-axis is temperature. Okay, the x-axis is time. The y-axis is temperature. So if we are going this way, okay, we are heating. That is, the temperature is going up. Okay. What happens if we're going the other way? Cooling. Okay, cooling. So we lower the temperature. This becomes a cooling curve. Let's look at water, because water is a substance we deal with every day in our life. Okay? So if it's a heating curve, we are increasing the temperature. If it's a cooling curve, we are... Yep. Okay. If it's a heating curve, we're going up. If it's a cooling curve, we're lowering the temperature. All right, a couple of things here. Q is what we're going to call heat. Okay, thermodynamics, lowercase q is called heat. All right, and if you heat, our Q is going to be negative. If you heat a substance to Q, is going to be positive. Okay, if you're adding energy to the system, it's going to be positive. Okay, you add energy, that value is positive. Okay, if you cool, what will be the value of the heat? Negative. Okay, and you see anytime heat is given off, where does it give it off to? It gives it off to the surroundings. Do you remember system and surroundings from Chem 1? Okay, anytime you heat something, you're heating the system, so that system becomes positive. If the system, which is the reaction, gives off heat to the universe, to the surroundings, then it becomes negative. If you give off heat, you become negative. Who takes that heat? The surroundings. Okay, so this is the sign convention in thermodynamics. Okay, so if you heat something, our heat Q will be positive. If you cool something, our heat Q will be negative. Okay, so just remember that. All right, so we'll make this for water. Okay, we'll start right here. Okay, we heat, heat some more, and then we get to A, point A on the curve. Okay, this will be for water. Okay, for water, this is going to be 0 degrees C. Okay, once you reach 0 degrees C, you become what? You not only become a solid, but what else starts to slowly form at 0? Liquid. Okay, so here we have two phases. We have a solid and a liquid, okay, at 0. Because what is 0 degrees for water? Not the boiling point, but the melting point. Okay. So here from A to B, okay, notice how from A to B we have a plateau. Okay, we're heating, heat some more. Here, the heat is overcoming the phase change. Okay, and that phase change is going to be delta H fusion. Okay, which for water is about 6.01. Okay, you don't have to memorize that. Okay. Aha, yes. We're at a temperature now where we are all liquid. Okay, we're all liquid. Heat some more until we get to C. For water, C is 100 degrees C. 100. What is 100 degrees C? Okay. So once you reach for water, 100 degrees C, what two phases do you have? You not only have liquid, but what also begins to start to form? Gas or vapor. Okay. So you heat some more, but notice that we're kind of like we're kind of stuck here. Okay, we're kind of stuck. This is the second phase change. And we heat some more, we heat, and we have to heat to overcome delta H vaporization. Okay, and for water, delta H vaporization is 40.79 kilojoules per mole. Okay, we heat some more, Ah, we've overcome this phase change. Now everything is vapor. Okay, there's no liquid. Okay, so that is when you heat. Okay, so to heat water, you have to overcome two phase changes. To cool water, you have to overcome two phase changes. Okay, we have a phase change 1. Okay, getting the solid and converting it all the way to liquid if you're heating. And for that, we must overcome about 6 kilojoules per mole. we heat some more, heat, until we get to 100 degrees, which is the boiling point of water. And then we have to heat a lot more, heat some more, heat until we overcome phase change 2, which is delta H of vaporization for 1 mole. For 1 mole, that's about 40.7 kilojoules per mole. Okay. All right, we'll start on this Monday, but let's just, in our last 3 minutes, let's just go over the pipeline. I just want to go over a pipeline, and then we can solve it on Monday. All right, calculate the heat released when 68 grams of steam at 124 degrees C is converted to water at minus 20 degrees C. So first of all, are we heating or cooling? We're going from 124 to minus 20. I think some parts in the Midwest reach these temperatures. If we're going from 124 to minus 20, are we heating or cooling? We're cooling. So what do you think our delta, or our Q is going to be? Negative. Okay. So we can plug it into this equation. I'll give you this equation on the exam. So if you're taking, the MCAT or whatever higher level exams, you're going to want to memorize this. Q equals ms delta T. Okay, where S is the specific heat. I'll give you this equation, and I'll give you the specific heat constants. Okay, we have the specific heat constant of water as a gas, the constant for water as a liquid, the constant for water as a solid. So how much heat is released when water cools? We're going from 124 to minus 20. Okay, in the last minute, we have to split this problem. Okay, how will we split it? Okay, we're going to calculate the heat going from 124 to 100 degrees C. Okay, we're cooling. And then at 100 degrees C, okay, what we must overcome? Phase change, which is delta H vaporization, and then we're going from 100 degrees to 0 degrees, and then we're cooling, remember, and then we cool to 0 degrees. What must we overcome at 0 degrees? Phase change, which is delta H fusion, and then finally we calculate the heat Q, and going from 0 degrees to our final temperature. What's our final temperature? Okay, so we have to sum up 0 to minus 20. Okay, so we're summing up. It's not just plug and chug. We have to sum up the heat going from 124 to 100, the phase change as it goes to overcomes 100 degrees, then 100 degrees to 0 degrees, then the phase change at 0 degrees, and then the heat going from 0 to our final temperature at minus 20. Okay, so we're summing up 5 heats. We're summing up 5 Qs. Okay, we're summing up 5 Qs, which is what we will do on Monday, right? Monday. All right, have a good weekend. I went 1 minute over time, so sorry about that.